are familiar with a merry-go-round. You guys know what I'm talking about with the merry-go-rounds? They don't have them much anymore because a lot of parks have gotten rid of them. But it looks something like this. No, it's not a sand dollar. So if I were to draw it from the side, does that look familiar? Something like that? They don't have them in many parks anymore. This idea that you could just go to a park and you and your friends could all jump up on the ride someplace and somebody else could spin the ride and jump on themselves, or maybe you all got around the outside, ran in a circle till it was going fast enough, then you all jumped on. They don't make those much anymore. You know, and, probably because people do stupid things with them, like bring their dirt bike in there and put the wheel up against it and spin it fast until the kids fling themselves off. Or maybe it's because moms don't watch their kids and their kids get their heads crushed here underneath the wheel, you know, of this thing. That's happened before. Or worse, they get flung off into the ethereal and there's like hypodermic needles in the park and stuff. I don't know what kind of parks you guys are going to, but, you know, or big piles of cat poop, or who knows. You know, there's no telling what kind of park you go to. But it's hard to find a park that has a merry-go-round anymore. You know, you can ride professional merry-go-rounds. They have those. Most of your theme parks will have something that will spin you around. But there's just something kind of awesome about riding this, right? You get on there and slide off, you know, get it going so fast that you're barely able to hold on. You wrap your arm around that pole as tightly as you could, and body's kind of flung out behind you, and you're screaming and yelling and all those little kid screams until finally you get flung out into the abyss. Sound familiar? Now, that's the first mistake. You don't actually get flung out into the abyss. People think that they're sliding backwards off the ride, but the only people who think that are the people that are on the ride. The people who aren't on the ride don't see that. What they see is that a moment before you let go, you were traveling that way. That's the direction you were traveling. At that instant, your velocity was that way, in the same way that this person's velocity is this way and this person's velocity is this way. They're on a circular object, but their instantaneous velocity is in that straight line. If they were to let go, which could happen, I've seen it done, the ride would continue to turn. They would travel on this last known straight line path. So after a few moments, they're over here. Right, that's where they are now. But the ride turned. So the bar isn't here anymore. All the bars have moved because the ride is spinning. The bars are now here. Now the other kids, we'll get rid of them for a minute. They're just in the way. But this kid, who is traveling in their last straight line path, look like they've gone from here to here. But they haven't. They've traveled in a straight line path that makes it appear as though they're being flung backwards, but they're traveling in a straight line. They let go, and because they let go, they travel in their last straight line path. Net force equals 0. They travel in the straight line. It's a trick of perception. Now, it's really hard because you guys have a lot of this perception built into you. If you don't believe me, only siblings understand what I'm about to talk about. You people without siblings won't understand it, but siblings live for the moment they're traveling in the car, and the car has to make a turn, and they're in the back seat, right? See, I don't even have to talk about it. You know exactly what I'm talking about, right? Now, if you guys who don't have siblings, you don't understand this game. For you guys with siblings, you've either been the smasher or the smashee, right? Is that what we're talking about? Yes, because you know you're going to make that turn, you smash your little brother or sister into the side of the car. Because for whatever reason, it seems like it works because you're turning. Of course it works because you're turning. Because you and your brother are traveling in the last straight line path. For me, it was a brother. I have a brother. The car is turning. So let's zoom in here a little bit. The car turns. That means you travel to here and your brother travels against the wall of the car. Car keeps traveling. Eventually, you won't be in the car at all. But of course, that doesn't happen because you are strapped into the car and there's doors and walls and things that keep you in the car contained. How do you think you stay traveling in the car if something doesn't push you this way to stay in the car? You feel like you're being flung out of the vehicle, but you're not. You're traveling in a straight line until you encounter something that turns you, that pushes you into the turn. I mean, maybe the grown-up version of this is not you sitting in the back of the car anymore. Perhaps the grown-up version is you're making that turn and your sunglasses or your phone sitting on the dashboard of the car. And you turn, you're over here, and your sunglasses or your phone is sitting over there because they went in the last straight line path. I guess I drew that a little wrong. And your car turned. Now, it probably didn't make it that far, but it probably appeared like it slid out of the car, right? You're turning, you're with the car, and your sunglasses slid across the dashboard towards the open window. You see what I'm talking about? Oh. Why did they suddenly go from sitting perfectly straight on your dashboard to flying out of the car? Was there something that grabbed them and pushed them out the window? That's what it looks like to you. Being in the car strapped in, it looks like everything in the car is suddenly moving to the outside edge of the turn. Put your soda, but didn't put it in the cup holder, it falls over. Your phone, which is sitting on the seat next to you, gets flung into the door. Right? As if from nowhere, this force grabbed everything and threw it away. No, it didn't. Everything was traveling in a straight line. The car turned underneath it. And if there was nothing to hold it in place, it stayed in a straight line path. Even the takeout food you're taking home to your family. Now, I seatbelted in because I don't want it flying out. I certainly don't want it flying into the wheel well when I slam on the brakes because of the idiot in front of me, who's probably you. I can only imagine. Now, the reason I'm bringing this up is because it's not a trick of perception. Objects obey the same rules we've talked about. If there's no unbalanced force acting on an object, it travels in a straight line. If you want the object to change the way it's moving, it requires an unbalanced force. That's still true. It has to be true. So we're talking specifically now about the difference between Newton's first law and Newton's second law. If an object wants to travel in a path that curves, the force is going to have to be unbalanced. It has to be. Otherwise, the object travels in the last straight line direction it was traveling. So let's say this car has a speed of 15 meters per second. And it's going to maintain it through the turn. So a few moments later, car has the same speed, 15 meters per second, but now it's traveling a little bit more to the left. This car clearly accelerated. When I say clearly, you might not see it as clearly, but it had to accelerate. And the reason is maybe not as obvious to you. Because if we look back at our definition of acceleration, we have acceleration would be the change in velocity divided by the time, right? One of your motion equations. Solved for acceleration. But if your speed doesn't change, then this is zero. That doesn't make sense. Well, there are other kinds of accelerations. That's the point. I said to you at the very beginning of the year, that acceleration is any change in velocity. This is a change in velocity. I'm no longer traveling the same direction. So my speed didn't change, but my direction did. We give this a special name. We call this a centripetal acceleration. A centripetal acceleration. Now, you've probably not heard that word before. It's not centrifugal. It's not centrifuge. It's not centrifugal. This is a different word than all three of those. Those words are not what's happening here. The word centrifuge is probably something you're aware of. You've probably heard the word centrifuge before. They use them to spin down blood when you give blood. They use it for a number of things. It is to create an acceleration by spinning something. But be careful about what that word really means and how to use it. The word we will use here is centripetal. It has a special meaning, which I'm going to get to. But centripetal acceleration is an acceleration that causes an object to change direction, but doesn't cause it to change speed. That's what centripetal acceleration does. It causes an object to change direction, but it doesn't cause it to change speed. Do I have to say that a third time, or is that good enough? Now, I want you guys to be thoughtful about things, but you're not always. Even right now, about 4 of you are completely distracted and aren't really paying attention. I want you to be mindful, though, because I'm going to start talking about something, and it's going to be out of left field, and you're going to wonder why I'm even bringing it up. But it's got incredible value to me. We did motion maps earlier in the year, and I didn't really pay attention to them very much. I didn't like them. When we talked about accelerations, we drew accelerations either in the direction of motion or opposing the direction of motion, to say that the acceleration made the velocity bigger or made the velocity smaller. So it would have been something like, acceleration that doesn't change the size of the velocity but changes its direction, which means there can be no component of acceleration in the direction of motion. No component of acceleration in the direction of motion. That means there's only one way the acceleration can possibly work, and that has to be either this way or this way. That's the only acceleration that has no component in the direction of motion. It's either perpendicular to the right or perpendicular to the left. Which one is most likely here? Which one do you think would cause the car's velocity to go in the direction of the turn? Perpendicular to the left or perpendicular to the right? I think it would be left as well. I think that makes the most sense. Which means that the only way the car actually turns is if the acceleration is pointed towards the center. That doesn't speed the car up and doesn't slow the car down. The only way the car turns is if there's an acceleration pointed at the center. The word centripetal means center pointing. That's what those two words mean. Center pointing. A centripetal acceleration is a center pointing acceleration. That means to actually make this turn, not only does the acceleration have to point towards the center, but it has to stay pointing towards the center, which means the acceleration has to keep changing direction. We will call this a radial acceleration, one that is always pointed towards the radius of curvature. A centripetal acceleration is a radial acceleration. Which also means I'm going to kind of change the way I talk about velocity. This velocity is a tangential velocity. It is tangent to the path of the object. A tangential acceleration would cause the object to speed up or slow down. A radial acceleration would cause it to change direction. There's a clear difference here. If you want to understand the vocabulary, I'll say it again. Tangential velocity is a velocity that is tangent to the path of motion. Tangential velocity. This object has a continuous tangential velocity, a velocity that is always tangent to the path of motion. It has a constant radial acceleration, an acceleration that always points towards the center of the radius of curvature. A tangential acceleration would speed up or slow down the car. A radial acceleration would change its direction. We're going to take a pause. I'm not making clear because I kind of hope that they would already be. This roadway I've drawn, it's a section of a circle. Do you see that? And that section of a circle probably has a radius of curvature out here somewhere, meaning that there is a point that would be considered the center of this segment of the circle, an arc length. When you've driven, you're aware of that perhaps, but maybe not aware of it as much as you'd like to be. But every single turn has a radius of curvature. And so a tight radius of curvature would be a harder to make turn than a large radius of curvature. Anybody who's driven South Mobley knows the difference, right? There are areas where you have to turn tighter. Those are going to have a smaller radius of curvature. Those turns are harder to make. So you need more acceleration to do so, or you need to slow down. You can be turning and slowing down or speeding up at the same time. Most of you are very aware of this because you hit the brakes too late when you go into your turn. Oh, damn it, I'm going too fast. I better slow down. Aw, I recorded that. Don't listen, moms and dads. Mr. Shelton's not a great teacher. So if you want to speed up or slow down, you can have an acceleration that's forwards or backwards. And you can still have one at the same time that have an acceleration towards the radius. You can do complicated things with your car. But understand, we're going to focus for the time being on situations in which the object's speed is not changing. We'll focus on that for the mathematics of this. So the object's direction is changing, but its speed is not. Of course, how do you calculate an acceleration like that? You can't use this. There is a special way to do so, and it's called the centripetal acceleration. I will write A with a little c next to it to indicate that it's a special acceleration, one in which the speed is not changing. It's the tangential velocity squared divided by the radius of curvature. So, speed of the car, radius of curvature. Now, this means something probably incredibly important, but you're going to miss it if you're not really ready. So I'll wait for you guys to get all that in there. This is how you calculate a centripetal acceleration. That's going to come up, clearly. Mostly through substitution a lot of times. But this is on your equation sheet, so it's not something you have to memorize. But there are other ways to do this too, so we're going to learn a couple of ways. Now, if you're really paying attention, you understand that every time you're dealing with a centripetal motion problem, you're dealing with Newton's second law. It has to be. For any object to change direction, it must accelerate, which means the forces have to be unbalanced. The only way the car makes the turn is if the forces are unbalanced. Period. The car doesn't make the turn if the forces are balanced. You will mess this up, so you need to be very careful. The worst thing is, there are no centripetal forces. You'll make that mistake, but I want you to hear this clearly. The forces acting on the car must be unbalanced. There must be a cause that changes the car's direction. There is no centripetal force, but there is a force that can cause centripetal motion. I'm going to say that very clear. There is no centripetal force. I'm not adding a force to your list of forces. But there are forces that cause centripetal motion. The forces acting on the car are all the same forces we've talked about already this year. There's weight, there's normal force, and there's friction. One of those must be causing the car to change direction. And you may know which one it is, you may not. I'll tell you this, anybody who's driven up north knows that if one of these is gone, you can't make the turn. Right? Icy roads, you can't turn. Which force disappeared when the road got icy? It is friction that causes this car to make this turn. And every car. Cars make a turn because there is a force of friction that acts on their tires that pushes them into the turn. Without friction, there will be no turn. There's no surface pushing in the direction of motion, and the weight is clearly not in the direction of motion. So the unbalanced force that causes the car to make this turn, got to be friction. Consider that the car is sitting on the roadbed. So here's the road, and here's my desperate attempt at a really bad car. It's a hamburger. So there's, tail lights. Looking at the back of the car. What forces do you think are acting on it? Well, it's going to have weight. It's going to have normal. What could possibly cause it to turn to the right? The only force left, friction. You turn the wheels and push them against the asphalt, and the frictional force causes your car to turn. And not just any friction, it has to be static friction. Do you really want your tires sliding against the road, or do you want them stuck against the road? I think most of you know you want them stuck. You want them rolling. You don't want to be sliding. So it's static friction that causes your car to turn. That might be a difficult thing to put together for now. We'll come back to it. This is based on friction. And not just any friction, it's based on static friction. Because it's based on static friction, you should be aware every time you turn, there's a limit on how fast you can make that turn. You may not see it all, but the limit's got to be buried in here someplace. Consider it this way. If the unbalanced force causing the turn is the frictional force, then that has to be true. Right? I just applied Newton's second law. At the same time, net force in the y direction is going to be equal to 0, which means the normal is going to equal the weight of the car. You guys following so far? Not doing anything weird, nothing new, right? If I wanted to talk about limits, then there are some clear limits about how I can make this turn. Consider doing those substitutions. When I do those substitutions, I find that m v squared over r has to be less than or equal to mu s times mg. And the first thing I'll point out is it doesn't appear that the mass of the car matters. Do you guys see that? You can get rid of that. But there's a clear balance here. If I'm driving the car, there are 3 things that are constant that I can't change during the turn. I can't change the radius of curvature of the turn, can I? Can I change the way the street is designed? Can I change gravity acting on the car? And I certainly can't impact the coefficient of static friction. That was decided when I put the tires on. If I want to successfully make the turn, then I better keep my speed under a certain value. Right? Less than or equal to. That's clear. You guys don't necessarily know this. I see you guys take those intersections. Let's think about that intersection, say at the one I see you guys at the most. Sheldon and Citrus Park Boulevard. Right outside the school. Because that's a crappy intersection, isn't it? You have to turn more than 90 degrees. It's about 110 degrees. You know what happens? You guys hit that thing going pretty fast because the light's turning yellow and you don't want to wait again. So you increase your velocity and you start to exceed. You can hear it, right? You guys have been there, hear those car tires screeching as they make the turn? That's being right at the threshold of breaking the friction. That's why you tend to make this bigger. You don't go from the leftmost lane to the leftmost lane. You open up and go to the right-hand lanes. Or maybe even hit the curb. Look at the curb next time you go. It's all covered in black smudges from you guys. Like this stopper on a string. With the stopper on the string, let's say that we are looking top down on the stopper on the string, okay? So that there's a piece of string and the stopper is traveling in a circular path. Not that path. Something like that. Now, when we consider the forces acting on the stopper, we really have, a couple possibilities. But the one that matters for moving in a circle is going to be tension. There's a tension force acting this direction. That's the unbalanced force that causes the stopper to travel in a circle. And that unbalanced force is responsible for the stopper experiencing a centripetal acceleration. I consider the forces in the x direction, I would say tension equals mv squared over r. So for the stopper, I know there's got to be a relationship between how fast I'm swinging it, what this radius of curvature is, and the tension there that's acting on the string. Clearly, if I make it spin faster, it's going to take more tension to get it to turn. Does that make reasonable sense? Now, do you understand that you could spin fast enough where you could exceed how much tension is available? Right? You can make the string break. There are limits to what we can do. In these problems, it's not going to be about, what is the velocity for it to have this amount of tension. It's going to be, you have a maximum amount of tension, how fast can you spin it? You guys who fish know that there's a maximum amount of force that the fishing line can take. It's right there on the label. When you buy that fishing line, if you exceed the amount of force the fishing line can take, it'll snap. If we were using fishing line for this, then we know that there's going to be a maximum speed. If we go any faster than that speed, we'll cause the fishing line to snap. We go back to the car is on the road. Terrible car there. Car is on the road, and it experiences an acceleration in this direction. I would have drawn something like that. That would have been clearly to indicate that if the velocity is this way and the acceleration is this way, then the object's velocity was probably going to become a smaller number. This was slowing the car down. Remember these conversations months ago?